But so to review, what we're going to cover today is, first, we're going to talk about the convolution operation. So kind of the basic mathematical operation behind convolutional neural networks. And then we're going to talk about some of the other important operations that make up ConvNets. And then finally, we're going to touch on quickly a classic ConvNet architecture. And then in the next part of the lecture, Sergey is going to talk about computer vision applications, and we'll go into more detail about other neural net architectures. So to review, first question we'll cover is, what's a convolutional filter? And then we'll talk about stacking convolutional filters and using these stacks to make up ConvNets. And then we'll talk about strides and padding. And we'll touch a little bit on filter math. And then finally, we'll give a couple of brief notes on how these things are implemented in the libraries that you'll be using. So what's a convolutional filter? I think the first thing to start with here is just sort of the inspiration, right? So, a question you might ask is, what's wrong with these fully connected neural networks that we've been talking about so far? Like, why are these not the right things to use for computer vision? And so to give you a little motivation for this, how would you think about applying a fully connected neural network to an image, right? So let's say that you have this grayscale image of a dog. Maybe it's 32 pixels by 32 pixels. So one thing you could do is you could just flatten that image, and that'll give you a vector of 1024 length. And then if you're doing some classification tasks that has 10 possible output classes, you can multiply that vector by matrix. So say a 1024 by 10 matrix, and produce 10 outputs. And that's kind of one way that you could do classification of an image with a neural network. Okay, so what's wrong with this? Yeah, and then so in this case, the matrix multiplication, those are the weights that you would learn. Well, one thing to notice here is that this is a really small image, right? This is 32 by 32, and we already have a 1024 dimension vector. So what happens if you start increasing the size of that image? So increase it to 64 by 64, you'll have 4 times as many dimensions in that tensor, which means you'll have 4 times as many weights to learn in your matrix multiplication. If you increase it to 128 by 128, it'll go up by a factor of 16. And so the dimensionality of the number of weights that you need to learn scales really poorly with the size of the image. And we want neural networks that we use for computer vision to be able to work well with larger images as well. So this is one issue with using fully connected networks for computer vision. Another issue is just, I would ask the question of like, whether you really need this many weights at all. So if you think about what this matrix multiplication is doing, for each possible output class, you're learning a weight, a separate weight for each input pixel in the input image, right? And so you're saying like each of those input pixels contributes, possibly equally as much to the value of the classification, right? And so in many images, there's maybe a few regions of that image that are particularly important to telling what's inside the image. So maybe this is really overkill. And then lastly, one other way you can see why convolutions are helpful is what happens if you slide this image a little bit to the right, right? So to us, it's pretty easy to tell that these are images of the same class, right? They're the same animal. But to a fully connected network, let's say the last pixel or the last row in this matrix multiplication always looks at the same pixel in that image. And so when you scale the image, it's looking at a different pixel, or when you translate the image rather, it's looking at a different pixel, right? And so just naively, without doing any form of data augmentation or anything like that, these networks that you form like this are not necessarily going to be invariant to translations of the input image. And in many computer vision applications, like image classification, for example, translation invariance is a property that we want our networks to have. So that's the motivation for convolutional filters. So the way a convolutional filter works is, instead of taking the entire image, flattening it into a vector, and then multiplying it by a matrix, instead you extract just a single patch of the image. So maybe you say, let's take a 5 by 5 patch of the image. So 5 pixels by 5 pixels. You flatten that, and instead of producing this massive vector, instead it produces a 25-dimensional vector. And then you take the dot product between that vector and another vector of the same length, and that gives you a one-dimensional output. So this is only looking at one part of the image. So how do you make it look at the entire image? Well, you can take this 5x5 patch and slide it across the image. So using the same weights, you can look at each different part of the image. And so you can slide it across the row and then across each of the rows until you get to the bottom right corner. And each of those operations is extracting a 5x5 patch, flattening it, multiplying it by a vector, and producing a one-dimensional output. And so if you combine all of those together, what you end up with is this output that has one corresponding output for each 5x5 patch in the input. Okay, so one question you might ask is, okay, that's like, I understand that's an operation we can do, but what reason do we have to believe that that operation can do anything useful? And so convolutions have been used in computer vision for a long time and were popular even before deep learning. And so if you carefully select the weights that go into that convolution operation, so the values of each of those weights, then you can produce effects like blurring an image. So this is a convolution that applies a blur operation. And there's a link here to other types of image kernels that you can take a look at if you want to build some intuition about what types of things these convolution operations can do. And the intuition behind ConvNets is that instead of like kind of carefully selecting each of the weights in this convolution, instead we're going to learn them. So one extension here is that in general, your image, we were looking at a grayscale image before. So it was 32 by 32, just one sort of value at each of those 32 by 32 pixels. But, for example, in RGB images, you actually have 3 values at each of those spatial positions. So you have the R channel, the G channel, and the B channel. So your input image is actually not 32 by 32, it's 32 by 32 by 3. And so again, if you wanted to classify an image like this using a fully connected network, you would need to flatten it, and you would have a vector that's 3 times as large as it is for the grayscale 32 by 32 image. And a similar thing happens with your convolutional filters. So if you're extracting a 5x5 patch of the image to apply a convolutional filter to, instead of just having 25 weights, that's going to instead have 75 weights because you extract each of the channels for each of those filters. But the operation is going to be the same. You slide this 5x5 by 3 window horizontally across the image and then along each of the rows, and you create an output. The input is not the only thing that can have multiple channels. The output can have multiple channels too. And so the way to think about that is that when we describe the basic convolution operator, we basically described it as a dot product, right? So you have this 5x5 by 3 patch of the image that is turned into a 75-dimensional vector, and then you take the dot product between that and another 75-dimensional vector to produce a single channel in the output. But instead of taking a dot product, you can instead have some number of convolutional filters that you learn independently of one another. And so instead of a dot product, you can have a matrix multiplication. And so in this case, you'll multiply this 75-dimensional patch from the image by a 75 by 10 matrix. And then you're going to produce an output tensor that is still 28 by 28. But instead of only having a single value on the 3rd dimension, which was created by this dot product, instead you're going to have 10 values on this 3rd dimension that's created by this matrix multiplication. One thing to notice here is that the overall format of the inputs and outputs to this convolution operation are the same. So the input to this model or to this operation was this tensor, which is kind of this stack of matrices that's 32 by 32 by 3, right? So it's this 3-dimensional tensor. And then after you applied these 10 5x5 convolutional filters to this image, you're left with something that's 28 by 28 by 10. So not exactly the same shape, but the same overall dimensions. It's still this 3-dimensional tensor. And so because of that observation, the output of this filter is equally valid as the input to another convolutional filter, right? So we can just take another convolutional filter and we can apply it to the output of this filter. So we can stack these convolutional filters or these convolutional layers on top of one another, and we can produce these like separate layers, just like you would have in a fully connected network with multiple layers. And so in practice, usually you won't just apply these layers one after another, because each of the layers that we described so far is just a linear operation. What you'll do instead is you'll apply a nonlinearity after each of the layers, just like you would after each of the layers in a fully connected network. So next, we're going to talk about strides and padding. And so these are different ways of changing the how the convolutional filter gets slid over the dimensions of the image. So convolutions can subsample the image. And one way that they can do that is by jumping across some locations, right? So in the examples that we showed before, if you have a 5x5 filter, then the way that you apply that is you first apply it to the first 5x5 like upper left corner of the image, and then you move over one pixel to the right and you apply it again, and then you move one more pixel to the right and you apply it again. What you can do instead, if you want to subsample your image, is you can skip some locations, right? So if you have a stride of 1, which is kind of the example we've been talking about so far, this is what it looks like to apply the ConvNet to the image. So you move 1 pixel at a time, and the corresponding output moves 1 pixel at a time as well. And so we do this across the whole image. If we add a stride to this convolution operation, what we're going to do is we're going to skip the second position that the convolution operates on. So we skip over that second position, and we do that in both dimensions because this is a 2x2 stride. And usually you'll see strides that are the same on both dimensions. So question I would raise here is, what happens if you want a bigger stride? So what happens if, say, you want a 3x3 stride? And so what that would look like is you would move the filter 3 pixels to the right instead of 2. And now all of a sudden the filter is kind of falling off the edge of the image. And so one way that we can solve this problem is by adding padding to the image. So padding is some default value that you add to the borders of the image, so that when you slide a convolution operator over those default values, over the edges of the image, you can still apply the operation. It just takes, for those pixels that are off the edge of the image, it takes that default value. And so this is kind of what this looks like. You have a stride and you're looking at 3 different positions on the image, but the edges are taken from a default value. And usually the default value that you pick is just 0. And so there's different strategies that you can use to pick how you apply padding. This is what's illustrated here is called same padding, and this is a pretty common form of padding that basically says, I want the output of this operation to be the same size as the input. All right, so this raises a lot of questions of like, okay, if I have an image that's this size and a convolution operation that, a filter that's this size and a stride of this size, how do I actually know what size my output is going to be? And one reason you might care about that is because if you're designing a neural net architecture, how you pick the next layer depends on what the size of the output of the previous layer is. So there's some basic math that you can use to calculate the size of the output of a convolution operation. And I'm not going to go through this in detail, but it's worth kind of just playing around with and getting familiar with if you're going to be using ConvNets a lot. A couple of notes here. There's a few parameters that you have. So one is the number of filters. So again, you're stacking filters. How many filters do you want? And typically this is set to a power of 2. So 32, 64, 128. But you can set it to whatever you want. There's different strides that you can pick. And so usually the way that strides are picked is that they're almost always the same for both dimensions. And they're usually 5, 3, 2, or 1. But again, there's other choices here if you want to play around with your architecture. And then for padding, the two types that you'll usually see are same, which we discussed briefly, and then valid, which just doesn't add any padding. And yeah, below this are the formulas that you can use to calculate the size of the output tensor, which is pretty intuitive, but it's kind of worth playing around with a few examples to get a sense for how these convolution operations actually downsample the tensors that they're operating on. And one last thing I'll mention on this, there's this great guide to the arithmetic behind convolution operations, which Sergey always recommends, and I've since checked it out and enjoyed as well. And so this is kind of like a very intuitive guide and has lots of cool, nice visualizations and equations that will bring you joy if you want to understand this stuff. So recommend checking this out.
I have a super quick question.
Sure.
Stuff like, well, so I'm assuming the answer is yes, but stuff like stride and like the specific convolutional operation, like, can it be learned? And I'm curious whether like the state-of-the-art ConvNets or image models actually have that stuff set by hand, or whether it's all just learned by at this point.
Yeah, it's a good question. I think like one way to think about it is for any sort of properties of the algorithm like this that typically you would consider hyperparameters. One challenge with learning them is that it's the operation of like how the stride, for example, affects the output of the model is generally not differentiable. So it's difficult to learn like in the inner loop of your learning process. It's difficult to learn just by like standard gradient descent methods. But a pretty sort of promising research direction that I think Peter will talk about later in the course is like meta learning or neural architecture search. And the way that those techniques work is kind of you have this outer loop of your optimization process. So the inner loop is learning a model with a specific set of hyperparameters on a specific task. And then the outer loop is selecting which hyperparameters allow you to perform best on this task. So there's a whole research field behind this. And that's kind of one way that people are learning things like, are learning hyperparameters for these types of algorithms. And I think that the state of the art on like quite a few tasks that are like very well studied, depending on when you look, tend to be like taken up by architectures that were learned via neural architecture search. But the other thing to note is that, typically those approaches are extremely computationally inefficient. And so in most cases in the real world, it's not very common to use them.
There's a couple more questions. Maybe it's a good time.
Yeah, we can pause here.
So someone asks, are conv filters always square?
They don't need to be mathematically, but I don't think I've ever seen an example where they're not. Have you, Sergey?
No. Yeah, they tend to be square. And then is there some property that guides us on how to choose filter size? Like would you use a 5x5 or a 3x3 or a 1x1?
Yeah, so we'll talk a little bit about this when we talk about receptive fields in a few slides. But I would say like there's intuition that you can build about what effect different filter sizes have on what the model can see and what types of outputs it can compute, which is what we'll talk about in a few slides. But just as a general philosophy, I would say that in deep learning, a lot of decisions like this are kind of guided by intuition about the way that these things work. But like the empirical results of other people who have studied these algorithms tend to like rule out over anything else. And so a lot of it is also just being familiar with what other people have tried and what works.
And then why would you ever want to use a stride that would cause the filter to move past the boundary of the image?
Well, so strides are useful for subsampling the image, which is, so different reasons you might want to do that. For example, if you're doing classification, your input image is really large. And so you want to, it's like 128 by 128. And the thing that you want to produce at the end is 10-dimensional. You need to get rid of a lot of those dimensions somehow. And so one way to do that is through strides. And then the question is, the question of like, why would you ever want to do something that goes over the boundary? One simple reason is just that it's like it's like you can't always make the math work to have the stride that you want without going over the boundary of the image. So that's kind of maybe one practical reason why you might want to.
Okay, that's it for now.
Okay, a couple notes on how these things tend to be implemented in some of the libraries that you'll be using. So again, let's think about the operation that we do when we're performing a convolution, right? So we're, and for the sake of example, let's say that the input is 5 by 5 by 3, so like a 5 by 5 RGB image. And we're going to use 32 filters of size 3 by 3 with a stride of 1, right? So remember that basically what we're doing is we're extracting each of the patches in this image and we're turning them into columns. And each of those columns in this case are going to be 3 by 3 by 3 or 27-dimensional. And we're going to do that for each position on the image. And what we're left with in this case is this 27 by 9 dimensional matrix. Right? So 27 is the extracted patch, and then 9 is each of the positions in the input tensor. And this operation in a lot of libraries is called im2col, so image to column. And then if we're taking a 3 by 3 filter, let's say we're taking a single 3 by 3 filter with 3 channels of input. So if you remember from the previous slides, that's the number of weights that you have to learn for that single channel output is 3 times 3 times 3 or 27. And then we have 32 filters. So we're essentially learning a matrix that is 32 by 27. And then what we're going to do is we're going to take this 27 by 9 matrix, which is all of the extracted patches. We're going to multiply it by this 32 by 9 matrix. Is this right? Or should this be? Oh yeah, sorry. So we're multiplying it by this 32 by 9 matrix. And then the result that we get from that is 27 by 32. And so we're just going to reshape that. So it's 3 by 3 by 32. Next, we'll talk about a couple of other important operations for ConvNets. And so the first that we'll cover are an operation that's used to increase the receptive field, which is dilated convolutions. First, what is a receptive field? So if you think about what the convolution operation is doing, you're sliding this window over an image and you're producing something that is generally lower dimensional. And so you can ask the question of, for a particular pixel, a particular position in the output tensor, which pixels or positions in the input tensor contributed to the weight of that output. So in this case, if we're looking at the center pixel in the output, since this is a 3 by 3 convolution, this 3 by 3 patch in the center of the image contributed to the value at that output. And so we say that the receptive field is 3 by 3. So each pixel in the output sees a 3 by 3 patch of pixels in the input. So one way we can increase the receptive field is by stacking convolutional operations. So in this case, if we have a 5 by 5 input and then we apply 2 3 by 3 convolutions, the last output sees all 9 pixels in the intermediate, and each of those sees 9 inputs in the original image. And so the receptive field of this single output in the input is all 5 by 5 pixels. And so just to review, stacking 2 convolutions one after the other increases the receptive field. And so one thing you can notice is that if you stack 3 by 3 convolutions, you get the same receptive field as a single 5 by 5 convolution. And a couple of nice properties are that in practice, this actually tends to perform a little bit better, maybe because you have an extra nonlinearity, even though there's actually fewer parameters, right? So there's 2 times 3 by 3 for the 2 3 by 3 filters, which is 18, and then there's 25 in the single 5 by 5 filter. So fewer parameters and empirically better performance. One other way to increase the receptive field is through dilated convolutions. So dilated convolutions are operations that kind of look like this. And so dilated convolutions increase the receptive field without increasing the number of parameters. And the way that they do that is by skipping pixels in the input. And so here you have a 3 by 3 convolution. So it still only has 9 weights, but it's dilated, and it's dilated by 1 pixel. So it's 1 dilated. And here it has a 5 by 5 receptive field. And so if you want to get like a really large receptive field for your task for whatever reason, then you can stack a bunch of dilated convolutions and the receptive field numbers will add up very quickly. Okay, so in addition to increasing the receptive field, one thing that you might want to do is to decrease the size of the output tensor, right? So why might you want to do that, right? So like, let's say that you have a large image as input and you want to produce a small vector as output, like if you're doing classification. Well, then somehow you need to take this, let's say 1024 by 1024 image and reduce it into something that's 10-dimensional. And so you need to, throughout your convolution operations, you need to try to decrease the size of the tensor. And so we'll talk about a couple of ways in addition to striding that we can do that. So one is pooling. The idea behind pooling is that you subsample an image by looking at a small rectangular region of the image and then sort of subsampling it by applying an operation to that region that reduces its size. And so typically this will either be you take the average of the pixels in that region, or you take the max of the pixels in that region. And in principle, there's other schemes that you can apply here, but these are the 2 most common. The most of all of those, by far the most common to see in computer vision applications is 2 by 2 max pooling. Right. And so what that looks like is you take each 2 by 2 patch and you replace that with a single pixel that has the max value of all the pixels in that patch. One other thing to note is that this is kind of less common to see now with state-of-the-art computer vision architectures. It was more common in sort of 2015, 2016 when deep learning was kind of exploding in popularity, but is recently fallen out of favor. And Sergey will talk in the next section about some of the other architectures that don't use max pooling. One other way to reduce the dimensionality of the tensor that we're operating on is instead of taking patches of an image and replacing them with a single value, instead, another thing that we might want to do is decrease the number of channels in the image, or in the tensor rather. And so let's say that we have something that's 28 by 28 by 192, right? So there's a lot of channels in that tensor. and we want to decrease it to something that's 28 by 28 by something smaller, like 32. So the way that this works is you basically apply a 1-by-1 convolutional filter to the image. So it's only looking at a single channel, a single pixel, but all of the values, like for all of the channels of that pixel. And you're still learning the weights, but the receptive field of each of these convolutions is just a single pixel. And so, like, if you want to think about conceptually what this corresponds to, it's like taking a single layer neural network, or like a single linear layer with some nonlinearity after it, and applying it to every pixel in the convolutional output independently. And this operation turns out to be pretty important in a lot of architectures that have been developed over the last 7 or 8 years. Last thing I'm going to cover before the break is just really basic kind of classical ConvNet architecture that you'll still see a lot, and we still actually recommend using as a baseline when you're starting new tasks. We'll talk about it in several lectures. And then in the next section after the break, Sergey is going to talk about more modern ConvNet architectures. But the most standard ConvNet architecture, like the simplest, like viable ConvNet architecture, is the LeNet architecture, or the LeNet-like family of architectures. So the way these architectures work is you take your image, then you pass that through a convolution operator, then you apply a nonlinearity, in most cases a ReLU, and then you repeat that option n times. So you apply n convolutions followed by the corresponding ReLUs. Once you've repeated that option n times, then you apply pooling, usually 2x2 max pooling. And then you'll repeat this entire process, so several convolutions followed by ReLUs followed by pooling, m times. And then once you've done enough convolutions and pooling to get your image down to a more reasonable size, then you'll apply some number of fully connected layers, so k fully connected layers followed by ReLUs, and then take the softmax of the results and use that as your output. And so the most common like kind of iteration of this that you'll see is the actual LeNet architecture, right? So in this case, this is used for MNIST. Your input is 32 by 32. You use 5x5 convolutions, stride of 1, 6 filters, very small number of filters. You apply a 10H nonlinearity because those were more in fashion when this architecture was developed. You apply average pooling because average pooling was more in fashion when this architecture was developed. Then you apply a 5x5 convolution again, this time with 16 filters, another 10H, another average pooling, and then you pass through 2 fully connected layers to get to the output. But in general, you can apply this type of architecture with any number of kind of convs and ReLUs followed by pooling operations, and then pass through fully connected layers to get like a reasonable baseline architecture for many image-related tasks.
Wait, I'm sorry. I got a little lost in your notation of like applying the convolution n times and the pooling m. Like, what additional benefit does doing it so many times give you?
So we talked about a couple of different ways of achieving like the same like receptive field, let's say, right? So one thing that you can do is you can apply a 3x3 convolution twice. Another thing you can do is you can apply a 5x5 convolution once. And we observed that like in practice, oftentimes applying 2 3x3 convolutions gives you better results than a single 5x5 convolution. And we sort of hypothesized that one reason why is that there's an additional place that you get a nonlinearity, right? And so basically when you're adding layers here, you're increasing the receptive field, you're adding additional nonlinearity, and you're adding additional learned weights. And so you're basically making the neural net more expressive, right? So it has more parameters to learn, larger receptive field, and more nonlinearity that is able to be captured.
So this is implying n times consecutively.
Yes, yeah. So to clarify,
Okay, sorry about that.
what
Sorry
this
about that.
describes is you take the image, and you have this operation which is like conv plus ReLU. You apply that n times consecutively, right? So each time applying that to the output of the previous one, and then you pool. And then for that entire operation, so n times conv by ReLU followed by pool, you can do that thing over and over again consecutively. Again, each time applying that entire stack of operations to the output of the previous stack of operations. And so you have this one tall stack of like many convs and ReLUs and pools. And then you use that to produce your output. Okay, and after the break, Sergey will talk about many more modern ConvNet architectures. But before we get to that, I'll pause and see if there's any additional questions.
Is there an activation function between the last two fully connected layers?
So usually you won't have an activation function. So there's usually an activation function between the fully connected layers, but you need to be careful about activation function after the last fully connected layer. And the reason that you need to be careful is that is a pragmatic reason, which is that in a lot of neural net libraries, the loss functions that you use expect the output of a linear layer, not one that has a nonlinearity applied to it. So yes, I would generally put nonlinearities between the fully connected layers, but then in practice, when you're implementing this, I would be careful about what you put after the last fully connected layer, and I would make that decision based on the loss function you're using and how that loss function is implemented in the neural net library that you're working with.
And then is the main point of ConvNets to limit the hypothesis class?
What do you mean by the hypothesis class?
I guess the space of like possible networks. I don't know.
In a sense, yeah, right? Like in a sense, you're saying you're sort of injecting some domain knowledge about the task of image classification, let's say, right? And that domain knowledge is that, you know, when you're determining the value of a particular sort of pixel in an intermediate layer or in an output tensor, then that depends more heavily on things that are close to it. Right? So things that are immediately surrounding it and a little bit further out than that. So in some sense, you can think of this as like injecting your prior about what the space of functions that might solve this problem could look like. And that could also explain why these things are so much more efficient to learn in practice.
And does pooling consecutively have benefits similar to applying conv layers consecutively?
So pooling consecutively, I think would just be kind of like applying a larger pooling operator, which empirically, I don't really see people do that. Like usually you pool, you do as small pool as possible, and then you like apply some more layers. So you add some more, you add ability of the neural network to like compute more stuff about each of the things in that tensor, and then maybe you'll pool again.
Yeah. Okay, well, I think that's it.